Today, we are going to discuss the next part, MSTR. The MSTR from SSTR. We are going to use the SSTR to get the MSTR today. Before discuss the MSTR, let me review the variance. The variance was the measure of the variation, right? Yeah, in the data, which was xi minus x bar square summation divided by n minus 1. I gave you 6 steps when we took the standard deviation instead 1. In that case, we take the mean, step number 1. We took the difference, step number 2, and take the square, step number 3, and take the sum, step number 4, and divide it by n minus 1, 5, and finally in step 6, we took the square root of it, right? We take the square root of it, step 6, then which was the S, that was the sample standard deviation. So in step 1, I gave you 6 steps to get the standard deviation. But now, we do not take the square root of it. So that will be the variance. That will be the variance. Okay? So please look at the variance. In the variance, please focus on the top one. Right? When I explain to you the variance or the standard deviation, here is an example. When I have a 1, 2, 5, and 7, we have 4 values. In step number 1, we have to take the mean, x bar, right? So I have to take the sum. The sum will be 15. Let me give you one more, yeah, to make it easier. It's a 0. And even still, the sum will be 15. And now we have to divide it by 5, right? So the sample mean will be 5. That would be 5. It's x bar. It's from 15 over, no, I'm sorry, it's not 5, it must be 3. Yeah, let me change. It must be 3. It's a 3 here. It's x bar. That is the summation 15 divided by 5, 3. Step number 1. What was the step number 2? Yeah, now we are discussing the variance, right? Yep. So step number 2 was take the difference. It was the distance. It was the distance from the sample mean. So the 0 case, that will be 0 minus 3 will be negative 3. And 1 minus 3 will be negative 2. And 2 minus 3 will be negative 1. In the right-hand side, 7 minus 3 will be positive 4. And 5 minus 3 will be positive 2. So when I take the sum, in the right-hand side, that is a negative 6. And the other sum in the right-hand side, did I say it's right? Left-hand side is negative 6. And another summation is 4 and 6. That will be positive 6 more. So simply I take the summation of the difference without square, always it must be 0, always. That is the reason why do we need a square. Because the -3 we have to make positive, -2 have to make the positive again. All negative distances, all negative differences, we have to make them to be positive, because later in step 4 we have to take the sum. Okay, so because of that, in the next step we take the square. So the 3 will be 9, -3 square as will be 9, -2 square as will be 4, and -1 square as will be 1. And the positive one will be positive, even we take the square. 16 as it will be, is a 4. Then now we take the sum. We take the sum of xi minus x bar square as will be positive. So I can have here is a 20, and there is a 14, 34. At the beginning, we had 0, 1, 2, 5, 7 samples. In step 4, we take the sum of the square. It's a 34. It is a sum of square. It is the sum of square. Right? You know, before, when we take the SSTR, you know, the SS stands for the sum of square, right? Yeah. So I want to compare the variance and the sum of square. Finally, I want to compare the MSTR and the variance. Okay? But the numerator in the variance, there was the sum of square. When we took the variance, we took the not only the sum of square, but the main part was the denominator, n minus 1. Can you remember what was the name of the n minus 1? It had the name degree of freedom. Simply, I can say it's a DF. Simply, I can say in the sum of square, we had the difference, right? How many xi's? You know, actually the xi's are the sample. So we had n sample minus x bar. You know, the x bar is a statistic. It is a single value. It's minus 1. Yeah. Simply, we can define the degree of freedom as how many first one and how many second one. We took the difference. That will be the degree of freedom. It's very simple. Okay? So please understand what was the structure for the variance. You know, simply I can say the variance was, we took the sum of square. We took the sum of square here, numerator, divided by the degree of freedom. That is the variance. So now let me copy the form. Yeah, I said the variance was defined as sum of square over the degree of freedom. Now we took the SSTR. It is another kind of the sum of square, because it was the double summation, basically xi bar minus x bar square. The other way, we describe the single summation ni times xi minus x bar square. Okay? If I can divide it by degree of freedom, it will be exactly same as the form of the variance, right? Then now we are going to name Mstr. So if I could divide by the degree of freedom, it will be Mstr, and it will be exactly same as the form of the variance. So now I can say the Mstr is a kind of the variance. It's kind of the variance. What was the variance? It's a measure of the variation. It's a measure of the size, right? We took the distance, square, take the sum. It's a sum of a square, right? So now the problem is, what is the degree of freedom? How did you get the degree of freedom n-1? We count how many xi's, first one, and we count is how many x bar. Additionally, we take the square and take the sum for the sum of square. But simply, we just count is how many xi's, that was n, and we had 1 x bar. Same idea, right? It's a something minus something. The things are the number of counts. Now, xi bar, it is the sample mean from each sample. Just a second, something wrong, right? Sample. What was the notation for the number of samples? K. The index of I from 1 to K, the index of I from 1 to K. So the K is the number of samples. And the sample mean from each. Then how many sample means do you expect? Say again? Oh, we had the 5. We had the 5, but generally, I need a notation. K. Because the K was the number of samples, and we can take the sample mean from each sample. So the number of sample mean is the same because we just take one value, the single statistic from each, right? So the number of samples means that will be K. How about the next one? It is the overall mean. How many? How many statistics? We are going to take the X bar, the overall mean. Please remind the homework problem we just reviewed before, right? So how many X bars? Just one. We took the single value, X bar, because that is the overall mean. So we took the only one as X bar. Yeah, so it will be the degree of freedom, K minus 1. So simply we just take the sum of square, SSTR, from the data set for ANOVA, and we define the degree of freedom. And simply we just take the fraction. It will be another variance named Mstr, right? Yeah. So please, I'm trying to understand how did we get the variance and why we have to take the sample mean. Now it is overall mean, right? And we took the distance, square, sum, divided by n, right? Yeah. So let me tell you more. It's about the variance. You know, here's the xi. Now is xi. Yeah, I'm explaining the variance again. So let me plug the xi, x1 here is x2 there, right? And we took the distance, and we took the square and sum, right? You know, when I erase the sum part of the variance, but still I just get the fraction. How do you think? What is this form? Summation over n. What was that? It was the form of the average. You know, the variance is on average. For what? The squared distance, right? But the variance was the measure of the variation. It's a measure of the variation, but actually it is the average. It is the average, the distance from the center to measure of the variation, right? So it's actually, it is the average, right? But now let me apply the idea in ANOVA. So now here is the x1 bar, x2 bar, x3 bar. Okay, let me take k equal only 3. When we have 3 samples, then we have a 3 sample means. You know, actually what we are doing in ANOVA, can you remember the null hypothesis? We want to compare the population means, right? But before, when we had, you know, the t-test, the pooled t-test or the 2-sample t-test, we had only 2 groups. So when we take the test, is the step number 1, step number 2. When we take the test statistic, we just take the difference. It's absolutely, we divided by the standard error. Yeah, it's a something. But basically, we take the difference. It's between the 2 sample means. But now, in ANOVA, we have a 3 sample means. So when I take the difference, we have to take the x1 bar minus x2 bar, x1 minus x3 bar. Even we take another difference between x2 bar and x3 bar. There are so many differences. So in this way, we cannot apply the procedures, right? But I cannot remember when, but early 19, let me Google, the Fisher is one of the most famous statisticians in history. He suggested the ANOVA for the first time. Think about the variance, right? So now let me give you another examples. x1 bar, x2 bar, and x3 bar, like this one, or x1 bar, x2 bar, and x3 bar. It is a case 1. It's a case 2. What we want to do? Always the null hypothesis is a mu1 is equal to mu2 is equal to mu3. Now, which one has a more chance to reject the null hypothesis? Case 1 or case 2? How do you think? Case 2, because there are a part is a more, right? So absolutely, the case 2 has a more chance to reject the null hypothesis. That means they are different from each other. But in case 1, they are put together. So it is easy to fail to reject the null hypothesis, not reject the null hypothesis. That means we agree they are same. So Fisher thought it's not the difference, but the variance. Okay, so when we take the variance from the overall mean, right? Which one has the bigger variance? Absolutely, the case 2. It has the bigger the variance. Probably it's a bigger SSTR, even bigger MSTR, right? Then what? Reject. We are going to reject the null hypothesis. The other way, smaller variance, we can expect a smaller SSTR, finally smaller MSTR. We are not going to reject the null hypothesis. In the conclusion, we have to say they are almost the same. So it is the idea in ANOVA. Okay.